Thank you for joining this session. This talk is about qualitative and computational analysis of chaotic behavior in a plasma system. This is Dr. Ahmad Hala from King Abdulaziz City for Science and Technology in Riyadh, Saudi Arabia. We will start by defining what is a physical plasma versus a biological plasma. The term plasma was introduced almost 90 years ago by Irving Langmuir, a major researcher in physical plasma history. One of his co-workers described how he gave the physical plasma its name because he noticed that the equilibrium part of the gaseous discharge that he was working with acted as having a fluid or carrying a substratum that takes particles of special kinds with it, much like the blood plasma. So he gave it this name. For the introduction of this talk, in any physical plasma study, the observed plasma source and the observation tools, the plasma diagnostics, are to be investigated as a system. We'll be using elements of chaos theory. By using these elements, we can investigate fundamental plasma physics phenomena mathematically, but using the mathematical abstraction of chaos theory. Some 30 years ago, chaos theory and its applications were popular. However, the studies of physical plasma problems gave results that describes chaotic behavior in plasma system, but without directly referring to chaos theory concepts. In the 90s, the reference to chaos theory concepts were explicit in the context of nonlinear dynamical analysis of physical plasma systems. In this talk, qualitative and computational analyses of chaotic behavior in plasma systems will be presented. The logistic aspect of maintaining the charged gaseous plasma state will be emphasized. We'll start with the qualitative analytics. We can see in this Langmuir probe trace, fundamental Langmuir probe trace, which is very main mean to measure plasma characteristics. It resembles the population curve, and there is even a linear resource line that intersects with two of the Langmuir probe traces. This resemblance to population, accounting for population, we can directly relate it to how we measure the charged species population of a plasma system. This is another data that was taken with the Langmuir probe. It shows a coexistence or simultaneity of two curves, two traces. This coexistent feature of two kind of charged species in a plasma is indicative of mixed transitive states of these charged species in the plasma, particularly as we approach the electron saturation region. Again, in that region, we can detect some instabilities, as people have done before. So we can see even some continuous bifurcation that's a signature of developing chaotic behavior. In the ion saturation region, we can, by inspection, we can even look at some saddle node bifurcation, continuous bifurcations, where we can identify points of repulsion and attraction that we can analyze the stability of the plasma system with. That's another convincing data that was taken just around the turn of the millennium, actually. Experimental data that shows the period doubling nature of thermionic plasma diode. And you can clearly see the chaotic behavior or the chaotic signature of the thermionic plasma diode. Using the model, actually, the computational model that we'll be using, basically we'll be using two models. We'll start with the logistic equation and its resemblance to the Langmuir probe trace, because Langmuir probe is one of the earliest diagnostic tools and still popular and still has ways to go in terms of interpreting its features based on elements from nonlinear dynamical systems such as chaos theory elements. The logistic equation, we can see here, the resemblance is clear, particularly for the positive numbers of R. Now, R is the rate of maximum population growth we will allow it to be negative in this model. If we do that, then we will it will yield something that's hasn't been detected up until now in terms of plasma behavior, but it can be. We can predict such behavior of plasma if we think about decaying in terms of decaying plasma population versus the growth of plasma species. When we allow for the positive R, which is the rate of maximum population growth, then again we'll see the resemblance of the so-called sigmoid function, or the counterpart in the physical world is the Langmuir probe trace. Now, what is X in this equation? X is normalized population number to kappa, which is the maximum sustainable population. So using this X, then we have a solution. The solution can be seen with these R possibilities. We can move now to the other aspect of the logistic interpretation of the behavioral plasma systems, which is the logistic map. The logistic map is basically a rule that is used before, a basic rule that was used before to generate random numbers. So you put in a number and then you get another number. And with abstract mathematics, there is virtually unlimited number of rules. But again, we'll be constraining ourselves to the basic logistic map or the basic logistic rule. Even with this logistic rule, this rule or map is capable of pretty complicated behavior. So again, with this map R here, it's called the biotic potential. That's another name for it within the logistic map context. The 1, 2, 3, 4 numbers of R here can be looked at as the reproduction rate of the species. This rate is directly proportional to the population size within the plasma. So that's another way to look at the plasma charged species population. The capacity kappa is again there, so we can normalize the total population to this capacity of the population. So, with the final closing remarks, this talk highlighted qualitative and some quantitative analyses of a plasma system chaotic behavior that originated from a physics treatment point of view. And this is the right way probably to conduct experiments by using chaos theory concepts. Is first to examine systems physically or naturally first and get a sense of an analogy of real world problems, and then implement the mathematically abstract concepts such as the chaos theory. We can even conduct stability analysis using the chaos theory toolbox to give us results that are faster and more intuitive than using classical mathematical tools. The Langmuir probe trace itself wants to be re-examined in terms of redefining its features, the need and saturation regions, and what is the definition or the meaning of the electron temperature or the ion temperature, and all these things should be looked at in a different context within a complete description of charged particles of the plasma system as governed by the logistic equation curve and the logistic map. The choice from abstract or specific mathematical chaos theory, again, models helps in tackling a wide variety of simple and complicated plasma physics problems that were treated before with classical mathematical tools. One last word that I would like to leave you in this lecture with is that modern and contemporary research methods and qualitative analysis techniques and research methods are to be introduced first as part of future scientific proposals to properly address major plasma physics issues without racing or rushing into developing concepts that are not well thought out. So
it's 6 o'clock.
The only way to do this is by implementing modern and contemporary qualitative analysis techniques and research methods. I published some of these findings about the qualitative analysis in my chaotic behavior paper. I'd like you to go back and look at it. Thank you very much.